All right, great. Recording is started. So good morning, everybody, and welcome back to Math 115. So I hope everybody had a great wellness day. Maybe let's start by everybody give me your rating. If you were to rate your wellness on a scale from 1 to 10, with 10 being the most well, how are we feeling today? 9. That's pretty well. That's okay. Some strong to medium strong wellness coming in. Nice. Okay. Not bad. Not bad. Okay. If I was gonna rate myself, I'd probably put myself somewhere at like a 7, maybe. Strong 7 would be probably pretty good. Reasonably restful weekend, but very stressful week coming up. So that's why I'd put myself there. Okay, cool. Well, hopefully your wellness was improved by the extension of the homework, which is going to be due tonight instead of the usual due date on Friday. There's another homework which is going to be due this coming Friday, which will be back on the regular schedule. So let me join this thing and get the iPad screen casted. Share screen. All right, sweet. Well, I guess move that one up there. I'll do a couple announcements real quick. And what are they? Homework, I don't remember the number. It's due tonight. That's March 1st. Oh yeah, your exam is on March 8th. Regarding that, same format. Practice exam soon. With regard to the practice exam, video solution as usual. Also, office hours as usual or by appointment. It would be great if like a lot of students have like a conflict or something, email me and throw out some times, and I can kind of try to find a time that I can get multiple people in one office hour appointment. So if you guys want some extra office hours, please just email me and I will find a time. I know there's a couple of students who've said they had a conflict of like another class when I have my office hours. So just email me, please. There's also SI sessions, or there's the regular usual SI sessions. Plus an extra review session. Okay, Jamie posted an email announcement about that just the other day. Well, yeah, when is the SI session for those? I got the email somewhere here. The SI sessions are Tuesday and Thursday from Tuesday, Thursday, from 6 to 6:50. And the review is on Sunday from 6 to 8 p.m. Okay, and my office hours are Monday 10:30 to 11:30. Excuse me, 9:30 to 10:30. 9:30 to 10:30. On Wednesday, 9:30 to 11:30. Okay, so that's about the exam. I don't think there's anything else except I want to remind everyone to please submit as a single PDF document. Okay, so you can use apps on the App Store that'll do this for you. Like I think it's called like Cam Scanner or something like that, or like My Tiny Scan if you're an Android user. And these things will just put everything into a single PDF, and it's important for you to post it to Blackboard as a single PDF so that I can use the Blackboard app to like write on your exam, so that you can get feedback for your exam. So that's that. Okay, so that's about the exam and the homework. Any other questions about that sort of part of the class? Okay, if not, I'm going to go back and remind you where we were. Oh, is that me doing that? Better make sure. No, I don't think so. Somebody might have a little bit of feedback going on their microphone. Maybe check and make sure that you're muted, please, unless you're asking a question. Okay. So where were we? We were talking about logs. And in particular, we were talking about special log rules. Okay, so we learned the product rule, which says that the log of a product is going to be equal to the sum of those two logs. Okay, so a little bit different than what we're usually used to seeing. And we saw the proof for that one. And then we also have the quotient rule, which says that if we do a log of two things being divided by one another, that's going to be equal to those two logs being subtracted from one another. Okay, and then the most important rule we learned was the power rule, which said that if we have log of x to some power, p, okay, then what we can do with that power is just move it right down in front. Okay, and we get p times log a of x. Okay, and this is like the entire reason that logs were invented, was so that we could solve for exponents in exponential equations. And you can see here, if we just get this exponent out of the exponent using a log, then we can solve for that p. Okay, so most of the time in a power rule situation, that we're most interested in what the power is. Okay, we want to know what the power is. All right. So I highlighted some common mistakes that students often make. And then we did a bunch of examples, and we learned finally change of base formula. Okay, so the change of base formula was a way that we can evaluate a logarithm with a base a, which is maybe non-standard, something like log 3, log 7, log a half. Okay. The way we evaluate that is just by evaluating ln of x. Okay, so the natural log of the argument divided by the natural log of the base a. Okay. And the reason that the change of base formula is important is that if you want to compute like log 3 of something, you'll notice that your calculator probably doesn't have a log 3 button. If it's an advanced calculator, it might have a log n button, but in most simple calculators, the only button that you're going to have is going to be the ln button. Okay, so if you want to evaluate log a of x, you're going to need to use your calculator twice. First to find, well, 3 times probably. First to find out what is ln of x, then to find out what is ln of a, and then to take those two numbers and divide them. And that is how you can find a logarithm with a sort of non-standard base. Okay. So there is one more example from this section that I wanted to get to, and it's this half-life problem. So I copied it into our next week of notes, and that's where we're going to start today. Okay, so this is going to be the last problem from the section which I didn't quite finish on Wednesday, and then we're going to start a new section. Okay, so what is the problem? It says we have some radioactive substance. Okay, so a radioactive substance decays according to the following equation. So we have A of t equals A naught e to the power kt. So if you're keeping score at home, this looks a lot like continuous interest. Okay, only there's going to be a pretty big difference with this equation, which is namely that this k here is going to be a negative number. And right now, TBD on the k. Okay, but the reason I know it's negative is because I know that this radioactive substance is decaying. Okay, so I'm having exponential decay here. Okay, and remember, if we have exponential decay on a continuous interest problem, that means that our k is going to be a negative number. Okay. So this is a little bit different than the continuous interest at the bank, because continuous interest at the bank is always modeled as exponential growth. And so we have this nice, positive number k. Okay. So here, this figure A naught, okay, is just the initial mass, and k is an unknown rate of decay. Okay, and we're asked to answer the following question. If 18 grams of this substance decays to 6 grams in 24 hours, okay, so after 24 hours, my original substance was 18 grams, and it's now 1/3 of its original mass, okay? We want to know what is the half-life of the substance. Okay, so let me get my pen here. Let's first determine what is a half-life. Well, a half-life is the amount of time t that it takes for a substance to decay to 1/2 of its original mass. Okay, so that's what a half-life is. And the way the question is packaged is sort of like they gave us the third life. They gave us the amount of time that it's going to take for this thing to decay to 1/3 of its original mass. Okay, so the game that I will play with this kind of equation is first to use this information to find out what is my rate of decay, k. And then once I have k and a naught, I can find out what the half-life is. Okay, I can find out by the half-life what the half-life is by just solving for t in this equation. Once I know k, the only thing unknown that will be left will be t, and I can use logs to solve that equation. So that's where we're going. And let's start by figuring out what is k. So I'm going to use this information here in this question, and I'm going to try to formulate that into an equation which is going to satisfy this equation which we said our substance follows. Okay, so it looks like we start with 18 grams. Okay, that's our A naught. That's our original substance. Okay, and here it takes 24 hours. So that means T equals 24 to decay to 6 grams. So this is going to be A of 24. So how can I write this down? I can write A of 24 equals 6 equals, well, A naught is 18, and I'll put E to the K times, remember T is 24. And now I have an equation in which the only unknown is this K here. So now I'm going to try to solve this equation for K. So what I'll do is I'll just divide both sides by 18 first. I have 1/3 is equal to E to the K, 24K. And now what I can do is just go ahead and apply the natural logarithm to both sides, right? So what happens if I do that? Well, I'll have ln of 1/3 on this side, and on the right-hand side, I will have ln of e to the 24k. Now, what do I get if I do ln of e to the 24k? How does that simplify? All right, Savannah says 24k. Does everyone agree? Okay, lots of agreement. Fantastic. Yeah, okay, that follows from one of two things. You could say that, okay, we could use the power rule to bring this down front, and then we'd have 24k times ln of e, and then that's 24k times 1. Or you could just kind of like, forget about using the power rule and just notice that we had a rule which said that if we do a log of a base e of e to some power, we just get the power, right? That's the entire thing about logs, is they're the inverse of the exponential. Okay, wow, I don't know why I have k up there like a power. I'm tripping. Okay, so we got 24k, and now we just solve for k by dividing by 24. We get ln of 1/3 over 24. Okay, so now we have what? We have a of t is equal to a naught times e to the ln of 1/3 over 24 times t, and that's it. Okay, so we have our equation. So now if I want to find half-life, we want to solve it ultimately for a time t. We want to solve for the time t such that a of t is equal to 1/2 a naught. Okay, we want to find the time t such that if we wait that long, the amount of substance left will be exactly half of our original substance. That's how we do half-life problems. So what am I going to do? I'll just put 1/2 here. A naught equals A naught e to the ln of 1/3 over 24 all times t. And I'm just going to solve this equation now for t, because t is now my only unknown. So what can I do? Well, first of all, I can divide by a naught on both sides. I'll just have 1/2 equals e to the ln of 1/3 blah, blah, blah. And I'm going to apply ln again. I'll have ln of 1/2 on this side. And on the right-hand side, I'll have ln of e to the ln of 1/3 over 24 times t. And just like before, we're just going to get the power. Ln of 1/3 over 24 times t. Okay, and now if I want to get t by itself, I just have to multiply by the reciprocal of this fraction, and I will get t is equal to 24 times ln of 1/2 divided by ln of 1/3. And that's my time. And now I can just plug into my calculator. I'm going to use Wolfram Alpha. If we do 24 times ln of 1/2, and then we take that whole thing and divide it by ln of 1/3, let's see what we get. We get 15.142314 blah, blah, blah. Okay, some really long decimal. I'm just going to round to, like, I don't know, 2 decimal places. This is approximately equal to 15.14. And we should use units, since we originally knew that our units were of time were hours. Oops, that's supposed to be highlighter. Hours. Then our final product should be 15.14 hours. Okay. So that's kind of a two-parter using the principles of logs. And essentially, the two parts were the following. We first used the information which was given to us in the problem in order to find out what the rate of decay was. Then, once we knew what the rate of decay was, we simply had to find the value t, which caused a of t to be equal to 1/2 a naught. Okay, and I think a lot of students, probably myself included when I started with this stuff, get a little bit confused, okay, because they start with the equation a of t equals a naught times e to the kt, and they look at the problem and they say, well, I know that a naught is 18, fine, but now I have an equation and I want this maybe to be 9. And they have this equation 9 equals 18 e to the kt, and they're like, what the heck do I do? I want to find the value t, which is going to cause this equation to be true, but I've also got this k value, which I don't know. And that's really going to throw a wrench in things, because if I have one equation with two unknowns, we know that can't be solved uniquely. So the goal here is, if you get to this step, you should recognize, oh crap, I have two unknowns here. I ultimately want to get that t, but I have this unknown k. I should probably solve for that first. Okay, so that's a day in the life of another pre-calculus student, not you guys, but some other pre-calculus student who would make a mistake like this. No, I'm just kidding. This stuff is tricky at first, so don't, don't be upset if you don't get it right on the first try. Okay, just take some practice. Okay, any questions about the half-life problem? Where did 6 come from? Yeah, 6 was A of 24. So in our question here, we had that 18 grams decays to 6 grams in 24 hours. So that means that if we plug 24 hours for t, then A of t, which would be A of 24, is going to be that 6 grams there. So this equation here is kind of describing that the third life of this substance is 24 hours. Okay. Well, if there's no other questions on the half-life problem, we're going to move on to the next section, which is section 3.4. And 3.4 is all about solving exponential and logarithmic equations. Okay, so we're going to have a few examples of how we do that. So for exponential exponential equations, we've kind of got two ways of proceeding. We can either solve by what I would call matching powers, okay, or we can solve these using ln, basically. Those are our options. And then we'll have an example about population growth. And then we'll learn some logarithmic equations and how to deal with those. Okay, and those usually wind up amounting to applying the log rules and then using exponential equations when necessary to get things out of the logs. Okay, so let's start with the first things first. So let's suppose we start with something like the following. So we have this equation 3 to the power x equals 27. And this is an equation that I think a lot of students in this class could probably already just solve just by looking at it. You can imagine what number x is going to cause this equation to be true. But what I want to do here is demonstrate the mathematics behind that intuition. Okay, the mathematics behind that intuition. So the point of this matching powers business is to express both sides as exponentials with the same base. With the same base. Now the left-hand side I'm going to leave as 3 to the x, and then the right-hand side I'm going to rewrite as 3 cubed. Okay, and if I can express these both sides as numbers with the same base, so exponential equation with same base on both sides, that's telling us that what? the takeaway here is that the powers must be equal. Okay. So we get x should be equal to 3. Okay. So these two powers should be equal. If you want to see the mathematics of why that is true, well, all you need to do is apply log 3 to both sides. Log 3 of 3 to the x equals log 3 of 3 cubed. And we know if we do log base a of a to a power, we just get the power. Okay, so that's why that's true mathematically. All right, so this is how we can kind of do this. Now, what I've kind of tacitly assumed is some foreknowledge that 27 is equal to 3 cubed, okay, which is kind of maybe putting the cart before the horse a little bit. So let me expand on how I went between 27 and 3 cubed and how you might do that if you don't recognize, okay, if you don't recognize that 27 is a power of 3. Well, what you could do is recognize that if you want to use this matching powers thing, you're going to have to get the same base on both sides. And the base on the left-hand side is already a prime number. So we're not going to be able to reduce that any further. So our only hope really is to reduce the right-hand side to look like a power of this hand side. So the first thing we might try to do is just take 27 and divide by 3. Okay, and I could write that as 3 times 9. Okay, and then you might see, aha, I know that 9 is actually 3 squared, so that's 3 times 3 squared. And I know using the exponent rules that 3 times 3 squared would be 3 times 3 to the 1 plus 2, should be 3. Okay, so that's how you could figure out this without necessarily immediately knowing that 3 cubed is 27. And the way you would figure it out is just by recognizing that since the left-hand side is already prime, we're probably going to have to write the right-hand side as a power of that prime number. And that's not really anything mathematical there. That's just the way that these equations tend to be set up. If they're going to be solvable, it's probably going to be like that. Okay, so this is our first line of defense, is to try to do this business, okay, and just set those powers equal to one another. Okay, so let's see another example of one where it's a little bit more complicated. So let's try this one together. I've got 25 to the power x is equal to 125. So remember, what I want to do is express both sides as exponentials with the same base. So let me ask you guys, what should the base be on both sides? Okay, we could try 25. You try 25 to the x equals, now let's try to express 125 as 25 to some power. What should the power be? Okay, revising the answer. I think we should use 5 instead as well. And here's why. If you try to use 25, this is kind of why I included this example. If you try to use 25, then you get a little bit stuck right at this step here, because you try to think, okay, now what should the power be, which goes right here, you know, and you think, well, maybe it's 2, but no, that's not true. That would be 625. And then you're talking about having to have like fractional powers, like, I don't know, 1.5 could work. I'm not sure. And you know, that just gets like kind of nasty. So a more elegant approach, maybe. Although I'm not going to preclude. I'm not going to say that that's not going to work out eventually, but it might take some work, and you might get a little bit stuck doing it. So I think what we should do instead is rather express both sides as a power of 5. So I'm going to rewrite the right-hand side as 5 squared to the power x, and I'll rewrite the right-hand side as just 5 cubed. Okay. After a while of doing exponential equations, you start to get a pretty good feeling for which numbers are perfect cubes, and 125 is definitely one of them, because 25 is 5 squared, and 25 times 5 is 125, right? 5 quarters, you've got $1.25. Okay. So now what should we do? Well, we can rewrite this left-hand side in a little bit of a clever way. If I've got 5 squared to the power x, what should I do with the powers here? If I do a number to a power to another power, how can I write that as 5 to a single power? So the question here is, should I multiply or add? Okay, we got some add. Anyone for multiply? Alex says multiply. Okay, so bit of a split here. Well, let's see if we can figure out what this should be. Let's, maybe I'll give an extra page. Okay, well, let's say we don't remember. Let's say we're doing an exam here and we run into something like this and we don't remember whether we should multiply or add. Well, let's just rely on mathematical principles to see if we can figure out which one it should be. Well, if I do 5 squared to the x power, what I really am doing to the x power, what I'm really doing here is 5 squared times 5 squared times ... times 5 squared. And the number of times that I'm going to do this is going to be x times. And then I know that if I had 5 squared times 5 squared times 5 squared like this, well, what I should do is if I had something like x squared times x squared, I know that that would be equal to x to the 4th, right? Because that would just be, I add those powers there. So this would ultimately be 5 to the 2 plus 2 plus 2 ... plus 2, where I do this addition x times. And if I do 2 plus 2 plus 2 plus 2 x times, repeated addition is the definition of multiplication. And so that's how I can see that what I should really do with these guys is actually I should multiply them. Okay, so if I have a number to a power and I take that entire thing to another power, I should multiply those powers. Okay, so just to review, if I have x to the a times x to the b, that's equal to x to the a plus b. But if I have x to the a to the b, that's equal to x to the a times b. for the reason shown above. Okay, so we should multiply. And if we do that, we get 2x. And now we have an equation which looks like 5 to the power 2x equals 5 cubed. So since I have the same base, I can just set the powers equal to one another. So ultimately, I get 2x is equal to 3. And therefore, x is equal to 3/2. Okay. So that's how we do that. So in this case, it wasn't quite as easy as just writing the right-hand side as a power of the base from the left-hand side. We had to rewrite both the left-hand side and the right-hand side to look like powers of a different base altogether. Okay, but the reason that I knew that we were going to go in this direction, and the reason that other students mentioned we should use the base 5, is by recognizing that both the left-hand side and the right-hand side are powers of 5. The left-hand side looks like 5 squared. The right-hand side looks like 5 cubed. If I see both the left-hand side and the right-hand side looking like powers, different powers of the same number, then that's a cue that we can use this power matching business. Okay, questions about this exponential problem or about how we multiply or add exponents when we're doing this stuff? Okay. If not, then I'm going to move on, and we'll talk about one more topic probably, and then close. Okay, and that's what to do if we want to solve an exponential equation with different bases. Okay, so let's talk about how we would solve something like the following. We've got 5 to some power 2x minus 3 is equal to 3 times some power x plus 1. Okay, and here's the issue. I can't match the bases. Here's why. I have no hope of expressing 3 and 5 as something like a to the x and a to the y, where x and y are integers. The reason is 5 and 3 are already prime numbers, which means they're not divisible by any other number, which means that if we want to write 5 as some number integer a to some power x, which is also an integer, our only choice is 5 to the power 1. There's no other integer combinations which will be able to write here. So here a, x, and y should be integers. I can't rewrite 5 as an integer base to an integer power except as 5 to the power 1. And the same is true of the right-hand side because 3 is also a prime number. The only way I can write 3 as some integer a to some integer power y would be 3 to the 1. And these two are incompatible. This is just, I mean, really, this is just rewriting what we originally had, right? So I'm in trouble here because the matching game is not going to work. So basically, if I was going to write down what the reason was, it would be I can't match these bases. 3 and 5 are prime. Okay. So what do? Well, we can still solve this equation by using the natural log. Okay, so I'm going to just apply the natural log to both sides and see what we can do from there. Okay, so if I take ln of 5 to the 2x minus 3 is equal to ln of 3 to the x plus 1, then there is a special rule, okay? I said it was the main reason that we even care about logs to begin with, which I can now use to simplify this equation. And let me ask you guys, what is the rule that I should apply now to these logarithms if I am hoping to eventually solve for x? Well, e is the base here of our logarithm, but I'm looking for one of those rules like the product rule, quotient rule, or the power rule. Okay, one of those rules for manipulating these logs. I think Om Kumar's got the right idea here. We should use the power rule here in order to take these powers and get them out of the exponent. That's kind of the real issue with this original equation, is the thing that I want to solve for, x, is tied up in these exponents. So I just apply the natural log to both sides because I know that's going to allow me to get that stuff out of the exponent and down front. So I'll rewrite both sides. This side is going to be rewritten as 2x minus 3, that's the power, times ln of 5 is equal to x plus 1, that's the power, times ln of 3. And now this looks a little bit funky. Okay, this looks a little bit funky, but we need to remember here that ln of 5 is just a number. Okay, we can plug it in on our calculator. We can do ln of 5, we'll get some decimal. And ln of 3 is also just a number. Okay, so I don't think anybody would have trouble if this equation said something like 2x minus 3 times 2 is equal to x plus 1 times 1. Right? If we had an equation like this, everyone would know how to use algebra to solve it. Okay, so let's not let these ln's confuse us. We know they're just numbers. And the way we manipulate these equations with numbers is just by using algebra. Okay, so that's what I'm going to do. So I'll get, well, how's the easiest way I can do this? Yeah, probably to multiply this out, I guess. So I'll get 2x, why don't I write 2 ln 5 of x minus ln 5 times 3 is equal to ln of 3 times x plus ln of 3. That's the distributive property. And then I'll move all the numbers over to one side and all of the x's over to the other side, and I'll get 2 ln 5 of x, 5 times x, minus ln 3 times x. And that'll be equal to ln 3 plus 3 times ln of 5. And then I will anti-distribute on this side, and I'll have 2 ln 5 minus ln of 3 times x is equal to ln of 3 plus 3 ln of 5. And then to solve for x, it's just a matter of dividing this number out. So I'll get x is equal to ln of 3 plus 3 ln of 5, all divided by 2 ln of 5 minus ln of 3. And the right-hand side now consists of a bunch of numbers, which we could plug into our calculator and find out what this fraction really is using Wolfram Alpha or a calculator or something, okay? All right, I think we're out of time, so I got to stop here. But does anybody have any questions about this stuff? Actually, let me say I'll stop here. I'll stop the recording. And if you have questions, you can stay after class. I have office hours starting now. So if you got to go, then go. Have a great day. And I'll see you all tomorrow. Otherwise, stick around and let your grievances be known.